Welcome to part 3 of geometrical optics. At this point we're going to start looking at lenses. A lens is a piece of material, usually glass or plexiglass, that's been shaped and has a index of refraction that allows us to focus light. What we have here is a converging lens or convex lens with a focal length of f. Now, converging simply means that if light comes in here, it then bends and goes through the focal point, which is a distance f away from the middle of the lens. Again, if light comes in parallel to the axis, it bends and goes through the focal point. So if light goes through the middle, it simply goes through the middle. That's all pretty simple. That gives us a focal length f, right? F is in meters. The power of the lens is given as 1 over f. 1 over f is in diopters, or 1 over m. Diopter is what you'll see your prescription in terms of when you go to pick up your glasses. So there you go. Power of a lens is 1 over the focal length. The focal length is the distance between the middle of the lens and the point at which parallel lines actually all intersect. And this is for a converging or convex lens. When using, skipped a page, sorry. This is a divergent or concave lens. Alright? Divergent means that when light comes in that's parallel to the axis, it turns and diverges depending on which side of the lens it is. Again, if it's going down the middle, it simply goes down the middle. If you were on this side of the lens, right, looking at it with your eye, let's give you some eyelashes, right? If you're looking at it, everything this side of the lens, you would actually see this focal point. But this focal point is virtual. And it's virtual because that's not where the lines of light actually cross, it's just where they appear to cross. The other thing about this, because the focal length back here is virtual at a virtual location, right? Then for a concave or divergent lens, the focal length is less than 0. So this distance would be negative for this lens. So we'll be using thin lenses. Now the thin lens approximation is pretty simple. What if we were not doing the thin lens approximation? If a ray of light hits the center of the lens, it goes straight through, right? It doesn't move at all. But if you remember from this drawing that we used earlier, right, if it actually just went straight through, it would come out the other side, displaced a little bit. Now, the thinner you make this lens, the smaller that displacement, right? So the thin lens approximation means we're simply ignoring that displacement, and we're treating the lens as if it were just a plane, but it still has curvature because that gives it its properties, its focal length, right? And again, here we have on this side, on the top, we have a converging or convex lens, and on the bottom a diverging or concave lens. For ray tracing for thin lenses, there are 5 simple rules. 1. A ray entering a converging lens parallel to the axis through the focal point f of the lens passes through the focal point, so it goes through here and then it hits this plane, right? You draw the line up to this plane, and then you draw a line through the focal point. A ray entering a divergent lens parallel to its axis seems to come from a focal point F. So we draw it to the plane, and then we look and say, oh, it would have come from here, so it goes like that. Alright, that's our ray trace for these 2 different lenses. Ray passing through the center simply passes through the center. If I could draw better, it would look better, but a ray passing through the center simply passes through the center. A ray entering a converging lens through its focal point exits parallel. So in other words, if I shine a light ray along and it goes like this through the focal point it comes out parallel. That's just the opposite path to coming in parallel and going through the focal point. And likewise, if a ray comes into a divergent lens headed towards the focal point, it comes out parallel. That's just retracing this path backwards. So those are the basic rules for drawing rays for thin lenses. So let's review for converging lenses, right? Let's just review. So here we are, parallel line. We're going to hit the lens, and we're going to go through the focal point. Now we're going to start at the figure's head. We're going to go through the middle, right? And then finally, we're going to start at the figure's head. We're going to go through the focal point, hit the lens, and then go out parallel. Well, when you put all of this together and you do all the parts, what you find is that these lines have an intersection point right here. Okay? Now, if we call the distance to the object DO and the distance to that image that we're going to draw right there DI, alright, then we get the relationship 1 over DO plus 1 over DI equals 1 over the focal length. That's pretty cool. Now the relationship between the height, H of the object, HO, and HI of this image here, right, is given by HI over HO equals minus DI over DO equals M. Why the minus sign? Right? Well, the minus sign there is because, well, what is the height of HI? HI in this picture, right? In this picture, HI, the height of the image. Oh, let's see if I can draw that better. In this picture, HI is less than 0, right? HI is 0. HI is negative. HI is negative in this picture. Alright, so the two basic equations, 1 over D0 plus 1 over DI equals 1 over F. HI, oh, that's not doing very well. HI over HO equals minus DI over DO equals M, and M is the magnification, right? M is the magnification. Okay. And you'll note, back to this for a second, in this case, in this instance, M is negative. And M is negative because it results in an image that is upside down. Now, for converging lenses, if the object is closer than a focal length, right? Closer than a focal length, then we draw the parallel line, right? Not an issue. Draw the line straight through, not an issue. But now, how do we draw the line, or where do these intersect, right? It turns out these now intersect at a point over here. Now, the light's not going there. That's just where it appears to come from. So this makes it a virtual image. In this image, or in this example, the distance to the image, right? The distance of the image is negative. Distance to the image is negative. Why? Because it's over here, away from where the light is actually going. And so 1 over D0, back to our equation, right? Oh. Alright, back to the equation. 1 over D0 plus 1 over DI equals 1 over F. Well, DI is negative in this case. Alright, so since DI is negative, we end up, because DO is less than the focal length, right? 1 over DO is greater than 1 over F. So 1 over DI has to be negative. Alright, onto diverging lenses. So ray tracing for diverging lenses is pretty straightforward, right? We're going to trace from the top straight in. That's going to diverge in a line that would go to the focal point. We're going to go straight through like so, and we're going to look at the focal point. What would happen if oh, we don't need to do that here. All right, so those two. Then where do they intersect? Right? And they actually intersect right here. We have exactly the same set of equations. Exactly the same set of equations for the converging versus convex lens, right? So 1 over d0 plus 1 over di equals 1 over f, and hi over these are exactly the same. A major difference is that di is usually, well, is always negative. The image is always virtual for a divergent lens or a concave lens. The image is always virtual, and in fact the focal length of a divergent lens is negative. So just a few notes consolidating some of this stuff. Distance di to the image is positive if the image is on the opposite side from the lens from the object, and it's negative it's on the same side of the lens of the object. That also makes it virtual. The focal length f is positive for converging lenses and negative for diverging lenses. If we look at the little table from the book, in case 1, f positive, d0 greater than f gives us a real image. Real image means you can actually project it onto a screen. It is positive, di is positive, the magnification is negative. Case 2, positive f, which tells us it is a converging lens, d0 less than the focal length, so the object is between the focal point and the lens. You end up with a virtual image. The di is negative, which means it's a virtual image as well. Magnification ends up being positive, and the magnification is greater than 1. With f is negative, or we have a divergent lens, the image is always virtual. Di is always negative. Magnification is positive, and m, the magnification, is less than 1. Alright, that's it for our first segment on thin lenses.